Hey, this is Chapter 6, Section 2, or at least the part of Section 2 that focuses on Lewis structures. And before we get started, I'm going to refresh your memory on valence electrons, show you how to do some Lewis dot structures of individual elements, and then we'll get into Lewis structures of full compounds. So if you recall, we're going to be focusing on the main group elements, so that's the S block there on the left, and P block there on the right. And in the previous chapter, we talked about valence electrons. So just a refresher, group 1 has 1 valence electron, group 2 has 2, that fills up your S block. Then going over to group 13, they have 3 valence electrons, group 14 is 4, and so on, all the way to get to group 18, which most of those have 8 valence electrons except for helium. We did talk about electrons want to lose and gain electrons, or atoms want to lose and gain electrons to be like your noble gases. That makes them much more stable. So we're going to show you moving those electrons around today, or sharing electrons, in this case whenever we get into our Lewis structures. So to start off with, we're going to look at electron dot diagrams of individual elements before we move on. Your electron dot diagrams represent your valence electrons. So for instance, if I have, we'll say carbon, when I look at the periodic table, carbon is in group 14, so it has 4 valence electrons. We're going to distribute its 4 valence electrons as dots. We want this to look 4-sided because technically your S block would be represented up here, and then your P block that has 3 orbitals could be represented on the other 3 sides. And if you remember, orbitals can hold 2 electrons each, so I could put 2 dots in each of those 4 sides. 2 times 4 is 8, so we would max out at 8. So with those 4 electrons, just don't put more than 2 per side. I've got 1, 2, 3, 4. I would be totally fine if you were even more realistic and you put the first 2 in S, great, and then 3 and 4. I would also be fine with, again, not necessarily what Hund would want you to do, but which would be the first one, but 1, 2, 3, and 4. So again, I've not showed you more than 4 electrons in any of the 3 examples, and there's not been more than 2 electrons per side. I could show you another dot diagram, let's say for helium. Helium is in group 18, but now helium's a little different because helium only has 2 electrons total, so we can't go more than just those 2 valence electrons. I could pick sodium. Sodium is in group 1, so how many valence electrons does it have? It has 1 valence electron. And let's do one more. How about sulfur? Sulfur is in group 16, so it has how many valence electrons? 6. So I'm going to show 1, 2, 3, 4, 5, 6. Again, I've only got 6 dots that represent the 6 valence electrons, no more than 2 per side. So those are electron dot diagrams of individual elements. You have to know how many valence electrons elements have based on the group that they're in for you to even attempt to be successful in our Lewis structures. So let's move on to our first slide we've got. So remember, octet rule. Oct means 8. Your atoms, or most of them, want to form bonds in order to have 8 valence electrons. So if they need to share with somebody else to get to that 8, they will do that. Now we do have some exceptions to the octet rule. Please write these exceptions down. The first exception is hydrogen. Now, hydrogen really can go with the next rule that we have, but hydrogen has one valence electron, and when it bonds to another atom, it can share an electron. So 1 plus 1 is 2. So that's how they are getting the number 2. But it is an exception. Hydrogen within a Lewis structure can only have 2 valence electrons, one of its own, and share one more. Now, the next exception, we'll get to these Lewis structures. The next exception is going to be any elements in groups 1, 2, and 13. So hydrogen's really up there above group 1, so it falls into this category too. We like to point hydrogen out just because hydrogen is in so many compounds. You'll see that exception over and over again. So let me explain what you're looking at down below. So if I have an element in group 1, there is one valence electron. Again, it could be sodium, potassium, rubidium, any of those. Their one electron will pair up with one more for a total of 2 within the Lewis structure. So when it says 2 right here, that's what they're talking about. It says it gets 2. Well, within the Lewis structure, yes, the element has one and will share one for a total of 2. If the element is in group 2, well, group 2 has 2 valence electrons. And guess what? Those 2 can share with 2 others. So 2 plus 2 is 4. And again, that's within the Lewis structure. And group 13 has 3 valence electrons. So group 13 has 3 valence electrons. And you guessed it, those 3 can pair up with 3 others. 3 plus 3 is 6 within the Lewis structure. Now, all of this within the Lewis structure will make more sense after you learn the rules for drawing the Lewis structures and we experiment with a few. And the next exception is called an expanded octet. So expand means more, so more than 8. The 3 examples of elements that can expand are sulfur, phosphorus, and xenon. Now, you'll see sulfur and phosphorus in several examples as we go throughout the next couple of chapters where they can expand. And again, they have the ability, but they won't always expand. You know, sulfur and phosphorus are happy with an octet too, but occasionally they need more room and they can expand. So, sulfur, being in group 16, has 6 valence electrons. So if it is going to expand, guess what? It'll pair up with 6 more within a Lewis structure and expand to 12 electrons within the Lewis structure. And then phosphorus. Well, how many valence electrons does phosphorus have? Phosphorus has 5 valence electrons, so if it expands, it would prefer to pair up with 5 more for a total of 10 electrons within the Lewis structure. Again, you will see examples of this before it's all over with. And there's a quick example. Again, you'll learn these. The last exception is radicals. This is where you have an odd number of valence electrons. I can tell you right now, and what we're going to do in this chapter, whether it's classwork, homework, quiz, test, I will never give you a radical. So one of our steps is counting valence electrons. If you ever come up with an odd number of valence electrons, you have done something wrong because I will not give you a radical. Okay. Please write down the 5 steps to drawing Lewis structures. Step number 1, find the total number of valence electrons. You will have a periodic table to look at. Hopefully you have a periodic table out right now. I mean, I'm looking at one. And within the periodic table, you've got to know what I pointed out at the beginning. Group 1 has how many valence electrons? Group 2, group 13. So you'll find your element, find what group it's in. You're going to know how many valence electrons each element has based on where it's at in the periodic table. So once you find that total, which is the single most critical step, when people mess up, they usually mess up with step 1. We then go to step 2, arrange your atoms. Singular atoms typically go in the middle. If you have carbon in your compound, it is always going in the middle. Carbon is the backbone of organic chemistry. Third step, you're going to form bonds between two atoms. So between your central atom and surrounding atoms, a bond is a dash. The dash represents 2 electrons. So a dot and a dot are the same as 1 dash. You can only have the dashes, though, between 2 atoms. The 2 dots, though, if that atom's not bonded on one side to another atom, you might have some of those free dots laying around. And fourth step, we will distribute the remaining electrons to give each atom an octet, except for the exceptions we talked about. So the biggest ones, if you have an element in groups 1, 2, or 13, they will always have less than 8 within the Lewis structure. So you have to remember that. And then the fifth step, if there are not enough electrons to go around, we're going to form double or triple bonds. So again, if you max out at 20 valence electrons, you've distributed all 20, and you need an octet, well, we're going to have to rearrange. So that fifth step is a if needed kind of thing, and if needed, we will rearrange dots to make dashes. So that dash that we looked at, we will rearrange dots to make dashes. Have these 5 steps handy. Have your periodic table in front of you. Let's go work out some examples. Example number 1, CF4. This is carbon tetrafluoride. Just getting my pens ready. So this math work we're going to do at the beginning, because the step 1 is find total number of valence electrons. I would expect to see this math for as long as we are practicing this stuff, up until at least test time. If you have to show it on the test, great. But if not, I'm hoping you're good enough not to have to do it come test time. But like I said, this is the number one place where people tend to mess up. So carbon, I have 1 atom of carbon. The 1 was not there. I just added it because it's understood. Carbon is in group 14. Therefore, it has 4 valence electrons because it's in group 14. 1 times 4 is 4. Fluorine, I have 4 fluorine atoms. 4 fluorine atoms. Fluorine is in group 17. So there are 7 valence electrons. 4 times 7 is 28. We add those up. We have a total of 32 electrons to find a home for. Again, I won't highlight this in pen every single time, but these numbers represent the number of atoms. The numbers off to the right represent valence electrons. So it's based on the group that element is in. Carbon's in group 14, fluorine's in group 17. Multiply, add up your final numbers. We have to find a home for 32 electrons. Second step, arrange your atom, singular atom in the middle. And again, there's carbon here, and it's singular, meaning there is only 1 carbon. So carbon goes into the middle of what our could-be 4-sided structure looks like. We try to keep things as symmetrical as possible visually. I have 4 fluorine atoms, so guess what? Keeping it looking symmetrical visually. There's my 4 fluorines. That is the second step. Third step says form bonds between atoms. Well, Between the central atom and the surrounding atoms, there are my bonds. A dash represents 2 electrons. How many dashes do I have? There are 4. 4 times 2 is 8. So I have taken care of 8 electrons just now. 32 minus 8 is 24. So I have 24 remaining electrons. In step 4, it says distribute those 24 remaining electrons to try and get our octets. Recall exceptions. Okay? Carbon. Is carbon in groups 1, 2, or 13? Nope. So it needs 8. Is fluorine in group 1, 2, or 13? Nope. So they need 8. When I count around carbon right now, carbon, those 4 dashes represent 8 electrons. It has an octet. It's full. We cannot put any more electrons around it. My fluorine, again, it's sharing those electrons. My fluorine only has 2 electrons around it. It needs some more electrons. We're going to distribute the remaining ones as dots. Again, keep it looking symmetrical the best that you can. And we're going to distribute. Always distribute 2 dots at a time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have just distributed the remaining 24 electrons. Now when you look around fluorine, I count, and let me just check mark them for you as I count. I count 1, 2, 3, 4, 5, 6, 7, 8, because that dash represents 2 electrons. So there are 8 electrons around fluorine. If you go look at the other fluorines, you will also see 8 for each one. I see 8 around carbon. But when I look at this, my total is still 32 total electrons. I have 24 dots, and the 4 dashes represent 8 electrons. 24 plus 8 is 32. There's no need to go to the 5th step. I don't have any electrons remaining, and everybody has an octet that should have it. So that's what the final looks like right there, which is what we had drawn. Let's go look at another example. Beryllium chloride, so BeCl2. Again, our first step is count up all of your valence electrons. There is 1 beryllium atom. Beryllium is in group 2, so it has 2 valence electrons. There are 2 chlorine atoms. Chlorine's in group 17, so there are 7 valence electrons. Multiply all of that, add it up. I have to find a home for 16 electrons, and you would show that math. Again, this is how many atoms of each element, and this represents how many valence electrons based on the group the element is in. Step number 2, arrange your atom, singular atom in the middle. Well, beryllium is singular. There's only 1 atom of it, so it goes in the middle. And I only have 2 chlorine atoms, the Cl2. I'm going to put 1 on the left and 1 on the right. You could put 1 on top and 1 on bottom. You could put 1 on top and on the left. Again, I try to make sure things are symmetrical as much as I can. That is step 2. Step 3, form our bonds. Well, between the central atom and surrounding atom, I can form 2 bonds. Those 2 bonds represent 4 electrons. 2 electrons per dash. So I'm going to subtract 4 over here. We have to find a home for 12 more electrons. Now, when we go to step 4 and we distribute the remaining electrons, it says recall exceptions. Chlorine. Is chlorine in group 1, 2, or 13? No. So it needs 8. Beryllium is in group 2. So if you remember, in group 2, they have 2 electrons of their own, and they can pair up with 2 for a total of 4. I currently have 4 electrons around beryllium. I cannot add any dots there. It is full, so that's an exception to the octet rule. So again, start on the outside. We'll make it look as symmetrical as possible. And as I do that, I need 12 electrons. 2, 4, 6, 8, 10, 12. There goes all 12 electrons. I have 8 around each chlorine now. 2 dots, 2 dots, 2 dots, a dash, that's 8. I have 8 on the other chlorine. Beryllium is an exception, so there is no need on this one to go to the 5th step. Let's go work out another example. And that's what that looks like. Next one, carbon dioxide. Okay, step number 1, we are going to figure out our valence electron counts. We have 1 carbon. It's in group 14, so 4 valence electrons. We have 2 oxygen atoms. Oxygen's in group 16, so 6 valence electrons. Again, our total is 16. Looks very similar to the previous one. We'll see if it works out the same way. Step 2, singular atom in the middle. That would be carbon. I'm going to put my oxygen on each side. Step 3, form your bonds. So the bonds are being formed between the central atom to the outside, and that used up 4 electrons. So I'm subtracting my 4. Got to find a home for 12 more. Step 4 says distribute those 12, recall exceptions to the octet rule. Oxygen and carbon, neither of those are in groups 1, 2, or 13. So all of them need 8 electrons around them. So start with your dots on the outside, and we'll work our way in. So those 12 dots are going to look like this. 2, 4, 6, 8, 10, 12. I just distributed all 12. As I look, I see 8 around oxygen there. 2, 4, 6, 8. I see 8 around oxygen here. Looks great. But around carbon, there's still only 4. And I need an octet because it's not an exception. So now we have to go to that 5th step. The 5th step says redistribute electrons. Can't add extra dots. I've got 16 total. But we can redistribute to form double or possibly triple bonds. So by redistribute, I'm bringing out my eraser. Bringing out the eraser. Right now it looks very symmetrical. Pull 2 dots. I don't care which set you pull, but pull 2 dots. If I pull off the left oxygen right here, great. I am now going to make a dash between that oxygen and carbon. So I pulled 2 dots and replaced it with a dash. I didn't add extra electrons. I just rearranged it. So around oxygen, I still have 8. 4 dots, 2 dashes, that's 8 total electrons. But around carbon, I went from 4 to 6. Next up, I have to do some more rearranging because carbon still does not have 8. So I'm bringing out my eraser again. To keep it looking symmetrical, this time I am going to pull the 2 on the opposite side. Pulled those 2 dots, I'm making a dash. Again, just rearranged. I still have 16 electrons total. Around this oxygen, there are 8. And when I look around carbon, I see a total of 8 because each dash represents 2 electrons. So there is your final answer for carbon dioxide, I have a double bond on each side of carbon, and you see your free electrons on each oxygen, and it still looks quite symmetrical. So you'll notice in this representation, they pulled the dots from the bottom side of each oxygen. That is okay. Numerically, everything still works out great. So let's go work through a couple more examples. We're going to add something called polyatomic ions. So far we've dealt with neutral compounds. Now you take what appears to be a compound and you put a charge on it. They're called ions, so a positive or negative charge. We're going to add a couple extra directions to our 5 steps. So step 1 is still find all of your total valence electrons, but now if it has a negative charge, you add an extra electron, and if it has a positive charge, you subtract an electron. If it had a 2 minus charge, you would add 2 electrons. If it had a 2 plus charge, you would subtract 2 electrons. And then we place brackets around the ion and label the charge that was given. So let's go look at an example. ClO4 minus. Again, counting up valence electrons. I have 1 chlorine atom. It's in group 17, so 7 valence electrons. I have 4 oxygen atoms. Oxygen's in group 16, so 6 valence electrons. And when I add that up, I get 31. Ooh, there's an odd number. That should be ringing some alarm bells. I have to go back and account for that negative charge that was given. And the rule was if it has a negative charge, that means it has an extra electron. So I'm going to add 1 more to my total for a total of 32 electrons. Now we go pick back up with our steps. Arrange your atoms, singular atom in the middle. Chlorine is singular. I have 4 oxygens, making it look symmetrical. Next step, arrange or form your bonds. So there are my bonds right here. That used up 8 electrons. So now I have 24 more electrons to find a home for. Oxygen and chlorine are not exceptions to the octet rule, so everybody needs 8. If you look around chlorine right now, it has its 8, it's happy, don't put any dots there. So those 24 dots need to go on your oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I used up all 24. No need to go to the 5th step here, which is make double or triple bonds. But what I am going to add is the next new step. It is a polyatomic ion, so we put our bracket right around the full ion. And we label the charge. It is the charge that was given. That negative goes right outside of the bracket. And again, your final answer will look something like this. I'm going to show you one more example. Again, you can go through it yourself. That's the ammonium ion NH4+. Adding up all the valence electrons, there's the 9. It's an odd number, but you have to account for the plus charge. So we subtract 1. When you set it up, nitrogen's in the middle. Form the bonds. That used up all 8 electrons because hydrogen is an exception to the octet rule. It has 1 and can pair up with 1 more for a total of 2. Put your brackets around it and label the charge that was given. So NH4+, the plus goes on the outside.